This meeting is being recorded.
In section 9 from chapter 13, we're going to begin a discussion here of what's called an enantioselective epoxidation, or formation of an epoxide. So what we've seen in the past is that we have an achiral starting material, so a an alkene that does not have a chiral center. But if we started with a chiral compound, there is a way that we could control our product formation. So what we've seen in the past, these epoxidation methods are not enantioselective. Um, but we do have stereoselectivity that we've seen when we start with a cis or a trans isomer to produce a cis or trans product. But now we are focusing on one enantiomer or another. So that would be at each chiral center, do we have an R or S configuration? So in general, if we have an achiral alkene, right, so these sites here, are not chiral centers. We could use either method. We could form halohydrin and then use base, or we could use a peroxy acid and we would generate this racemic mixture. So this happens because either plane above or below, rather either face of our alkene can have epoxidation occur. So we would need a chiral catalyst to be used in order to perform an enantioselective epoxidation. So we would favor only one enantiomer over the other. So we can accomplish this by using what's called a chiral catalyst. So this would select one face for the reaction to occur, either above the plane or below the plane. And what we see here is this scientist, Sharpless, was the first to discover that if we use a chiral catalyst, and specifically this chiral complex of this titanium tetraisopropoxide and DET, diethyl tartrate, we would use only one enantiomer of this DET, either the positive or the negative enantiomer, in addition to this titanium tetraisopropoxide here. And this catalyst would cause this enantioselective epoxidation of an allylic alcohol. So this is what Sharpless discovered, and this is how we utilize these chiral catalysts, so that if we used a positive enantiomer for the DET, we could form our epoxide above the plane. So we can keep track of our R groups, R1, R2, and R3, and this epoxide formation above the plane. If we use the negative DET enantiomer, then we would form our epoxide below the plane of the pi bond. So this is our mechanism that's shown, and we generate that enantiomeric excess in about 98% for each of these reactions. And again, depending on which enantiomer of our DET catalyst we use, the positive, again, will form above the plane of the double bond, and the negative DET would form our epoxide below the plane. And that's how we see the differences in the enantiomer that results as our product. So we'll continue with the next section in our next video.